Hi everyone, it's Clara and I'm back with another one of my science videos. So I haven't done any of these little science explanation videos for a few weeks, I realise. And that's just because I did a couple of interviews that I really was excited about and I wanted to get out. And then I've just been really busy. I've been reopening my lab. And so just finishing off one of these talks, these whilst with my sort of rant videos, I can just sort of talk, and with my chats, obviously I need the time, but with these I've got to actually put the animations together, so it takes a little bit of time. So so I've been busy, basically, is what I'm saying. But anyway, we're back, another one, and this will sort of finish off my uses of superconductors for now. Not quite sure what I'm going to talk about next, but I suspect it'll be how we manufacture superconductors, how we're making them, or the ones that we're working with, how they're made. So I think that'll be next, but just be aware it can be a few weeks before these come out. I have got another one of my science chats recorded, and it would be lovely to start podcasting them as well. That's pretty easy to do. Most podcasting services cost money, and I don't have much money, unfortunately, but I've been told about a free one, so I might give that a go. So that'd be really exciting. And, the usual, like, follow, subscribe, tell your friends, that's, support me. And then, like I say, I don't have much money. So anyway, that sounds a little bit beggy. I don't want to be begging. Yeah, just, support me if you want to support me. And, if I'm good enough. Maybe I'm not good enough. Anyway, let's go on with the video, shall we? I think. Alright, cool. So, superconductors. Hey, brilliant. So, what we're using them for this week? Well, fusion energy. So, fusion energy. So, when we're talking about fusion energy is one way of producing energy, potentially. We can do it, we're just not very good at it yet, right? As a society, as a planet, whatever. We're not quite there yet. And this is sort of real long-term science. Now, fusion energy will be a clean energy source, so it's a good reason for doing it. And it's and if we can get it right, there's a lot of bonuses. We won't be using, coal. We won't be digging up Earth resources. It'll be great if we can get it to work, and it'll be safe. Unlike nuclear energy, there's no waste products. Everything just breaks down real quickly, and so it's safe. I'm not saying that nuclear isn't safe, but we do produce stuff that we have waste products. So this is a way of doing it. But like I say, we're not quite there yet. So there's a whole bunch of different ways of making fusion energy, a whole bunch of different fusion generators. I'm going to be talking about tokamaks. So I realize that there's different types of tokamaks as well, like spherical ones. I'm going to be talking about more classic tokamaks. And there's three big ones that I'll sort of probably talk a little bit about. One of them is JET, which is in Culham in the United Kingdom. So that's a big international collaborative project. That's been running for a few years, and I'm really lucky enough to have seen them sort of fire it up. Been there when they fired it up, which is really cool, because it's not too far away. And then there's a big one in China called EAST. So that's been running for a few years or something like that. It's that's one that's just being tested out at the moment. And so JET has a lot of sort of records for fusion energy so far, and then EAST has the longest plasma, so I'll sort of mention that a little bit. And then there's ITER. ITER is going to be built in France, and they've actually just started building it. They've just started building it now. So these things aren't quick, they aren't fast. They take a long time. I'm guessing that there's probably something in the United States as well, but or North America, but I don't know what they are. So sorry about that. That sounds a little bit weird, doesn't it? Anyway, so yeah, what is fusion energy though? I said it's this clean fusion energy, way of producing energy. What is it? So if we take our hydrogen atoms, right? So we've got our hydrogen, or we can strip an electron from hydrogen. It's not too hard. So hydrogen is a proton in the nucleus. So there's this nucleus which is a slight positive charge. If we strip the electron, then we've got an ion all of a sudden. So we've got this hydrogen, and we've got this positive nucleus. And if we try and bring them next to each other, what's going to happen? I think we probably can guess. Yep, they're going to repel. They're going to repel because they both have slightly positive charges, right? So that's because we've got this electric field, which is green in my diagram, coming out of the nucleus, and then we've got these rings around, which is the magnetic field. So yeah, when we try and put them next to each other, they're going to repel. But just if we can get them close enough to each other, if we can overcome those repulsive forces, then we can actually get them close enough, and they combine. When they combine, they release a whole bunch of energy, and we've got a new particle. But the main thing is we release a whole bunch of energy, and that's what we want to do with fusion. So the real key is, how much energy do we have to put in order to get more energy out? That's where it gets a little bit tricky. But how are we doing it, first of all? Well, probably no surprise, we are using, of course, superconductors. And we're actually using superconducting coils. So we've talked about superconductors when we were talking about the Large Hadron Collider and CERN. So what we said was that we've got this coil of superconductor, and then we can squish it together, and we've basically got a ring of superconductor. And in this case, rather than a perfect sort of circular circle, we've got like this D-shaped ring. And we put a whole bunch of these next to each other, so that once again, a bit like CERN, we're making a huge donut. We've got loads of these all around. So they go all around, and we call these the toroidal coils. Now, just like CERN, the whole purpose of these superconductors isn't to sort of provide energy or anything. It's to have this high magnetic field. This magnetic field means that in this case, it's our plasma. In CERN, we're talking about sort of particles. We're creating this magnetic field, this really strong magnetic field, which means that our plasma in this case has to stay within this certain track. So in the case of a fusion generator, it's within the middle of this D-shape donut. I guess it's I wanted to use the analogy of like the jam in a donut, but that doesn't really work with a ring donut. Can you have jam-filled ring donuts? I don't know. Anyway, let's move on. So we've got this. We're using these strong superconductors because it allows us to create very high magnetic fields which confine our plasma. Brill. What else are we doing? Well, we've also got more superconducting coils. That's right, we want more superconductors. So we've got these big, huge rings around the D-shape, around the donut. The donut that's made of all these D-shaped superconducting coils. We've got these extra rings all the way around it, all the way around the diameter. And this generates another magnetic field, another strong magnetic field. But in this case, it's in a different direction than the one, because these are coils in one plane and these are coils in another plane, which means that they're creating a different direction of magnetic field. So we've got these two magnetic fields. And I should say that I think ITER is going to have 6 of these rings around it. So there's not just the one, there's a few of these, and these are the toroidal coils. So we've got these two magnetic fields. Now, why do we have these toroidal fields? Well, it's kind of, I said that the toroidal coils, they sort of have this circular magnetic field for the particles, but the truth is that some of the plasma will manage to spin out and it will manage to reach the walls. And the truth of the matter is that a plasma is hot. It's releasing so much energy. If we get fusion energy right, we're releasing so much energy. That's exactly what we're talking about doing. That's exactly what we're trying to do. But we're going to release so much of it that we cannot make an interior chamber out of something that won't melt. So by having this magnetic field around the inside, which will help us with our plasma, and then we have these toroidal fields as well, it twists the plasma. So the plasma doesn't necessarily just go around in a circle, it sort of twists, and that keeps it away from the walls. We want some of that energy to get to the walls because we want to recover that as energy, but if all of our plasma is able to sort of spin out and hit the walls, we just end up with a melted mess. So that's why. So we've got these two magnetic fields. Now, that's once we've created a plasma, that's how we sort of stop our system from melting and how we confine it. But we've still got to generate it. So we've got other tricks. Let's think. Let's use, I don't know, some superconducting coils. So what we do is we drop in a central coil. So this is a huge coil, superconducting coil up the middle. And I should say that these things are meters, tens of meters. These are huge pieces of kit, and the distance between the toroidal coils and the central coil, you're talking millimeters. These are really well engineered precision measurements being made on huge bits of kit. So we're dropping in another superconducting coil. Go figure. Now, remember what we said about superconducting coils. If we apply a potential difference between two ends, we generate a current. And we know that depending on which direction that current is traveling in, it creates a different magnetic field. Because if the current's going in one direction, there'll be a magnetic field in one direction. If it's going in the opposite direction, there'll be a magnetic field in the opposite direction. So with this superconducting coil, what we're doing is we're basically turning it on, passing this huge current through it, generating this magnetic field, and then we're shutting it off. And then we're turning it on in reverse. We're basically shaking the current. So we've got this additional magnetic field which is going up and down, up and down, up and down. So we've got a circular magnetic field, we've got one that's going up, and this all combines together to twist our plasma. And then what we're also doing is in the middle, we've got this magnetic field which is alternating up and down, and we're doing this quite quick. So we're basically, what we're doing is we've got a big box and we're shaking up all our hydrogen. It's as simple as that. We're introducing our hydrogen and we're giving it a good old shake. The magnetic fields are stopping it hitting the walls, and we're using other magnetic fields to shake it up. And when we do that, we actually get some of our hydrogens to collide. How cool is that? So we actually get them close enough because of all the energies involved. Like, we actually manage to overcome some of those forces, and so some of them collide together, and boom, we release energy. And as we release energy, there's more energy available. Some of that gets used by nearby particles that are also being shaken, so they combine and they release energy, and it cascades. So some happen, and then more collide, and then more collide, and we're producing more and more energy. And I should say, I said this was safe. We can turn this off. You remove some of this, like the current and stuff like that, it'll die out. It'll die out in milliseconds, seconds. It'll turn off very quickly. It's not like nuclear power where you can have this cascade, and if the walls rupture, it'll all thing. No, like, if we did anything to upset this system, it's just going to quench. It's just going to turn off. So it's nice and safe. And like I say, hydrogen, we've got loads of hydrogen. So it's the most abundant element on the planet. So this is cool. Like, this is a really good way of making energy. So yeah, we're releasing this energy, and some of the energy we leach off, and that's our energy recovery. But you can probably imagine that this takes an awful lot of work. Like I say, it's not an easy thing to do. It's not an easy thing to power, and at the moment, we have to put more power in than we're getting out in return. We with superconductors we can have persistent coils, but with this fusion energy system we still need an awful lot of energy. Like this isn't a persistent the central coil isn't a persistent current, it's up and down, so it takes a lot of energy. So we're not quite there at being able to produce more energy than we put in, but we're trying to get there. And we're doing that with, there's all sorts of other little tricks we can do as well, because one of the things we can do is Do we have enough superconductors? No? Let's introduce more superconductors. So what we can do is we can introduce a particle accelerator, which is a superconducting coil, which we've talked about in a previous video. And so what we can do with this is we can introduce these charged particles. In this case, we're not talking about hydrogen, we're talking about deuterium. So deuterium is an isotope of hydrogen, and it's naturally occurring. Like we can get it from seawater. There's like a not insignificant amount of this naturally available in the ocean. So we can take this deuterium, and what we do is we just fire it in. We just whack it in there. So we're shaking up this plasma, we're shaking up all this hydrogen, and then we're firing these extra deuterium atoms in, and they want to break down a little bit more easily. So we're just adding more things in there, and so hopefully we're getting to the point where the energy we put in is less than what we're getting out. And so there's this paper. I pulled out a paper. There's a link on screen. The paper name on screen, and it's really cool. They have these images of the inside of the jet fusion generator, the jet tokamak, and so we can see that there's big, huge D-shaped chamber. The central coils will be down here, and then the toroidal coils will be around the whole thing. And like I say, when you turn it on, you get this really cool confined plasma, which, because of the toroidal and toroidal coils, it sort of twists and turns, and there's this beautiful image in this paper. So like I say, check out this paper, and they talk more about, they're talking about it in more detail. It's really cool. And yeah, so like I say, jet in column, so far it's achieved 16 megawatts out for 24 megawatts in. So yeah, we're not quite at parity yet, but we're moving towards it. We're moving towards parity. The energy in is the energy out, but what we want is more energy out. And we're also only doing it for short amounts of time at the moment, because there's still these worries about melting the walls. So we've got to make sure everything's, we don't want to melt the system. And so actually the longest plasma so far is East, which is the one in China that I talked about. They ran a plasma for 10 seconds, and that reached 100 million degrees. That is hot. 100 million degrees Celsius. Yeah, that's hot. That is toasty. So that's why we don't want it touching any of our equipment. That's why we're trying to keep all our plasma away from the walls. It's hot. But yeah, we take some of the energy away. So like I say, we're building ITER at the moment. ITER started building. It should be finished by 2024. And then we're hoping to have fusion power running in it by 2035. And then hopefully we'll have some results on what it can produce by 2040, which means that we're just about to start building it. It's been in works for years. We won't have results for 20 years yet, if everything goes well. And that's interesting, because fusion generators, they might not work, but we are spending billions and billions. We are spending so much time, so much effort. The scientific community is working on this. We are spending our fortune on this stuff. And it might not work. But can you imagine if it did? If we can put energy in and get more energy out, can you imagine what that will mean for energy production going forward? So it's worth us trying. It's worth us putting the energy in. And this isn't really necessarily related to this talk, but I just think that that's a really interesting thing, whereas we're willing to do that to try and make energy by fusion, but we're not necessarily willing to do that when we talk about improving the atmosphere for scientists. We're not talking about improving the culture for people in science, because that's seen as too much work, too much effort. And yet look at fusion generators. When we talk about that, we're willing to put that money in, we're willing to put the effort in. So I think that's a really interesting point. So that's fusion energy. It'd be wicked if it works. It'd be really wicked if it works. Fingers crossed. I don't know. Hopefully it'll work, but like I say, it's I think East will really improve our understanding of what's going on. Jet, I think they're upgrading the magnets, maybe. So this is the thing: as we improve our superconductors, we can improve the magnetic fields that we produce with our superconducting coils, and so we can improve the magnetic confinement, which means that we can, worry less about melting our system, our tokamak. So we need to improve our superconductors to help forward this, and we have been doing that. So it will have new superconductors in there, more modern superconductors than Jet, and the same. It's the same with East, and then Jet. So Jet, there's still a lot more work to be done at Jet. Jet is not finished; it's not done. Like they're gonna continue putting out new data and finding things and pushing the boundaries and improving the engineering, improving the superconductors, and increasing what they can produce. But we've also got these other systems as well, which is really cool, and that's what it's going to take to really crack fusion energy, right? Worldwide collaborative research. We can't just, it's not just going to be one research group that figures this stuff out. Like, we've got to collaborate. And I touched a little bit on collaboration in some of my science chats with various people. But we have to collaborate because we're not going to crack everything. And if we could crack fusion energy, that'd be wicked. So, yeah. Yeah, so that's that basically. So like I say, I think there'll be a science chat out next week, and then that's with my dear friend Shazia Ishmael, and then I'll start putting out a video on like I said, maybe the history of superconductors, or how we in my lab are sort of making superconductors, or how are the superconductors we're working with made. The thin film ones, bulk meh. Anyway, that's all for me for today. Thanks so much for sticking with me and watching. Like I say, like, subscribe, share, that's kind of cool. But otherwise, I'll see you next time. Take care, and yeah, bye bye.